I'm going to go over some select problems from the Math 3 Unit 1 Worksheet 1, starting with number 3. Here we're asked to graph and use at least 3 points to label any asymptotes. Oh, and to label any asymptotes, if there are any. Remember, we have 4 different kinds of graphs that we're working with here. We have the linear, the exponential, the quadratic, and the absolute value. And so part of this is also recognizing what we're working with here. In number 3, we don't have the absolute value sign. We don't have the squared sign, no x squared here. So it's not quadratic, it's not absolute value. We also don't have an exponent, where the variable is your exponent, so it's not exponential. So number 3 is a linear function, and if you have an x and a y, solve for y first. I'm going to do that by switching the equation around and writing 3y is equal to 2x, and then divide by 3. And we end up with y equals 2/3 x. So this is linear. And we're just studying parent graphs right now, and for the linear parent graph, we know it's going to cross through 0, 0. So 0, 0 is a point, looks something like this, right? So I'm going to put a point at 0, 0. And we can check that. If I plug in 0 for x, I end up with 2/3 times 0 equals y, and 2/3 times 0 is 0. Anything times 0 is 0. So we can verify that 0, 0 is a point. But as stated here, we want to get 2 more points. So we can pick another value. So let's say 3. If I plug a 3 in to this equation, I end up with y is equal to 2/3 times 3. When I multiply this, I end up, when you multiply a fraction with a number, you could change that number to a fraction, the integer. This is 2/3 times 3 over 1. You multiply the numerator with the numerator, denominator with denominator, you end up with y is 6 over 3, which reduces to 2. So when we plug in a 3 for x, we get a 2 for y. And so I'm going to plot the point 3, 2. And really, once you have 2 points, you know what your line is going to look like. Another way we could have come up with this point is if you have some understanding of slope. Notice our slope is 2/3. So from the point 0, 0, I could have went up 2 units and to the right 3 units. So you can use slope when working with a line to find another point. You can also just pick a value for x and plug it in and get another point. Also, when you have fractions and you're selecting what x value to choose, pick something that you can see. My denominator is 3, so I want to pick a value that I can divide by 3. So I picked 3 for x, and it worked out with just some nice integers. So if I were to pick another number, I'm thinking, what can I divide by 3? I could pick a negative number. I like -3. If I picked another positive number, I'd pick 6. So I'm going to try that. I'm going to plug in a 6. So when x is 6, I want to figure out what y is. So I'm going to plug in 6 for x, and I get y is 2/3 times 6. When I multiply that, I end up with 2 times 6, which is 12, divided by 3, which comes out to be 4. And then I plug in the 4, that's my y value. And I can plot that. So I'm going to go right 1, 2, 3, 4, 5, 6, up 1, 2, 3, 4. And again, we could have used our slope. Notice you go up 2, right 3 again. But these points should line up because this is linear. And there's our graph. For number 6, it's the next one I'm going to do. Notice that this is quadratic. which makes the graph of a parabola, or a U-shape. And it's a parent graph, and if you recall from our notes, the quadratic parent graph goes through the point 0, 0. You can test that out if you want. If you plug in 0 for x, you end up with y equals 1/2 times 0 squared. Following order of operations, 0 squared is 0. You end up with 1/2 times 0, and anything times 0 is 0. So you see that 0, 0 is a point that we can use. I'm going to pick another point. Notice we have a fraction with the denominator 2, so I'm going to pick something I can divide by 2. 2 is an easy choice. So I want 2 to be my x value, and if I plug that in, I get y is 1/2 times 2 squared. Exponent first, so that's 1/2 times 2 squared. 2 squared is 4. And 1/2 times 4, you're going to only multiply the 1 and the 4 together, and you end up with 4 over 2, which is 2. So 2 comma 2. And remember that first point is the center. It's, you have this axis of symmetry, or this symmetry in this quadratic. The right side is curved. This is the right side of the U shape, and you have a matching left side, and so we'd have a point here at -2, +2 right here. And if you want, you can check that out. If you plug in -2 for x, you're going to get y is 1/2 times -2 squared. Be careful to have that -2 inside the parentheses. We want to square all of that. And when you square -2, you end up with +4, and you end up, that's exactly what we had here. So we end up with the same result of 2. And so those are our 3 points that give us a nice sketch of that quadratic in 6. Number 8, notice the variable is in the superscript. We call that an exponent. So this is an exponential function. Now, the parent graph of the exponential function does not go through the point 0, 0. Actually, what it has is a horizontal asymptote, which I'll mark here, and that goes through the point 0, 0. It's actually the line y equals 0. That's my horizontal asymptote. That's not part of the exponential graph, but it gives shape to it. The exponential graph, I'll graph in green here. The parent graph always goes through the point 0, 1. And why is that? Well, if we plug in 0 for x into our equation, we end up with y is 2 to the power of 0. Anything to the power of 0 is 1. So 0, 1 is a point. With the exponential function, you're going to want to pick values to the right of that first point. So you're going to want to plug in x values that are positive. If you plug in a negative x value, you're going to end up with a fractional answer because the shape is going to get closer and closer and closer to 0. It's a little harder to graph that way. You won't end up on integer points, or we call them lattice points. So I'm going to try plugging in a 1 for x. If I plug in a 1 for x, I get y is 2 to the power of 1, which is 2. So I plugged in a 1, I got a 2, so my next point is 1, 2. And I'll do one more point. I'll plug in a 2 for x, and I end up with y is 2 to the power of 2, which is 4. So when x is 2, y is 4. Plot that point. And this thing is growing exponentially. And number 9, we have the absolute value sign. That's your two vertical lines enclosing that x there. That's what we refer to as the absolute value sign. The absolute value, the graph of an absolute value, will, we should say linear absolute value. There are other types. But the graph of a linear absolute value creates a V shape. You get the vertex of that V is going to be at 0, 0, and you're going to have a line protruding from that point to the right and another line to the left, and it creates this V shape. So we say it's linear because it's made of two lines, or parts of two lines, and it's the absolute value sign. So this goes from here. To pick a point, notice we have a fraction with the 3 in the denominator, so I'm going to pick something that we can divide by 3, which I'll pick 3. I'm going to plug a 3 in and I get y is equal to negative 4/3 absolute value of 3. Take the absolute value of 3 first. Absolute value just doesn't do anything to a positive number, so it's going to keep it positive 3. I'm going to multiply the negative 4 and the 3 and get negative 12 over 3, which comes out to be negative 4. So I plug in a positive 3, I end up with a negative 4 as an answer, and so that's a point that this graph goes through. So positive 1, 2, 3, down 1, 2, 3, 4. And so I know that's one side of the V. This is symmetric, so here I went down 1, 2, 3, 4, right 3. If I go down 4, left 3, I find another point automatically to create that symmetric V shape. We can test that out. If I try out negative 3, I get y is equal to negative 4/3 absolute value of negative 3. The absolute value of negative 3 is positive 3. Absolute value changes a negative number to a positive number. And then we're going to end up with the same work as we had before. This would be negative 12 over 3, which is negative 4. Before we leave this problem, I want to point out, because this is linear, there is a slope that you can work with. And that slope is the negative 4/3. And if you remember how to work with that, it's a negative, so you go down 4, right 3. So that is the slope of the right side of the V shape always. If you go back to number 8, 8 does not have a slope. So no matter what you know about slope, you cannot apply it to number 8. You also cannot apply slope to number 6. A quadratic is rounded. It doesn't have a constant slope. So the only time you can use slope is with something linear, like number 3, or something, again, we got linear absolute value, which is number 9. So anything that contains lines, straight lines, you can use slope with. I'm going to skip now to 15. 15 is a special case. It only has an x variable. There is no y variable. This is linear. But not only is it linear, when you have an x equals a constant, it's going to be vertical. If we had y equals a constant, it would be horizontal. So it's going to go through the x-axis at 5. So locate 1, 2, 3, 4, 5 on the x-axis, and you draw this vertical line. The reason it's vertical is if you pick any point on that vertical line, any point, and look at its x-coordinate, all the x-coordinates will be 5. Move on to number 18. The instructions here are to give the domain and range for each of the following graphs in both inequality and interval notation. So I'm going to start with inequality notation. And I'm going to use a capital D for domain. So domain deals with your x values, and your x-axis goes left, right. And so we're going to look at this function and ask us, well, if we were to make those arrows continue, how far left would it go? And this thing's going to go as far left as we want, and to the right as far right as we want. So it's going to cover everything. And so for, there really is not an inequality to write here. And so for inequality notation, I'm just going to write all real numbers. For the range, I'll use capital R. Now we're looking at the y values. Range deals with y. And we're going to ask, well, if we continued this graph forever, how low would it go? And here it's got a boundary line that it's not going to go below. We call that a horizontal asymptote. It's actually not going to touch it, and that's happening at a depth of -3. But it's going to go as high as we want. So it's got to be anything bigger than -3. And so that's what I'm going to write. All y values bigger than -3. You don't want to say bigger than or equal, because it won't touch there, but just greater than. Now we're going to rewrite this using interval notation. Okay, so for interval notation, for the domain, we know it's all real numbers, meaning it goes as far left as we want, so -infinity on the left side. How far right? Positive infinity. And whenever you use infinity, use parentheses with that infinity. For the range, here the lowest value is always on the left side, highest value is on the right side when you're doing interval notation for the domain or range or anything else. Whenever you do interval notation, always do smaller to larger. So the smallest value is going to be -3, and I'm going to use a parentheses because the parentheses indicate it's not going to be equal to -3. It's just your boundary starts there. If I want it to equal -3, I'd put a bracket. And then it's going to go as high as we want, so all the way up to infinity. And always use parentheses with infinity. So let's try this again with number 23. Number 23 is not a shape that we've looked at. Actually, looks like we have a piece of a line here and maybe a piece of a parabola, or it could be, it's rounded, it could be maybe an upside down exponential function. Either way, we're going to try to give the domain and range here. So first, let's work with inequality notation. So for the domain, it goes as far left as 1, 2, 3, 4, 5, -5. Doesn't equal, you got that open circle there. If it was colored in, it would equal, but because it's open, it doesn't equal. So I'm going to use parentheses. Sorry, I'm doing interval notation right now. Not inequality. Let's do inequality first. So it doesn't equal there, but it will go as far right as we want. Right? It'll just keep going this way. I mean, it goes down and to the right. And so everything bigger than -5 is what we'd like to write. And so that's all your x values, domain's x, greater than 5. For the range, what's the lowest? As far low as we want, so -infinity. What's the highest? Well, the highest looks like it's at 1, 2, 3, 4, And notice it's colored in, so it actually hits 4. So all y values lower than or equal to 4. To write that in interval notation, for the domain, lowest to highest. So lowest is negative infinity. Always use parentheses with infinity. The highest is 5, but it doesn't. Sorry, I messed up there. Let me fix that. I'm on the high and the low. Domain, how far left, how far right. So the furthest left is negative 5. The furthest right is infinity. Use parentheses on both because it never hits infinity, it never hits negative 5. For the range, the lowest is negative infinity. It's the lowest y value. The highest would be 4 and actually hits 4, so use a bracket. The next section, we're asked to write the equation for the following graphs. Let's look at 27. 27 is that special case. If we go back and take a peek at 15, we said vertical lines look like this. We got x equals whatever that x value is for them. So if we apply that now, just work backwards on 27, it's going to be x equals, and if you pick any point on here, they all have the same x value at negative 4. This is linear, but a special case, this is vertical. Okay. 29 I want to do with you. 29 is quadratic. It's not, like if you look at 28, 28 is absolute value because you have that sharp V, that pointy part, right? Where here 29 is more rounded, and so that's how I know it's quadratic. And so we know when you're writing a quadratic, it's going to be y equals something, I'll let it be a right now, times x squared for the parent graph. And that's all we're studying right now. But I need to figure out what a is equal to. So can't finish yet. I need to know what that is. To find that, use a point that's not at the vertex. So I'm going to use this point here. The vertex won't be helpful. If I plug in 0, 0, it won't help me find a. And you could try it, and you'll see why it's not helpful. But pick a point that's not on the vertex. So that we have the point, what's this, negative 1, 2, 3, 4. So negative 4, negative 2. So I'm going to plug in negative 2 for y and negative 4 for x and solve for a. So we end up with negative 2 is equal to a times positive 16. I'm going to, this is the same thing as negative 2 is equal to 16 times a. If you feel more comfortable switching that around, you can. I'm going to divide both sides by 16, and you end up with negative 2 divided by 16 equals a. So a is going to be, I'm going to reduce that fraction, divide top and bottom by 2, and I get negative 1 over 8. So my equation is y equals negative 1 over 8 x squared. Okay. So again, I started with y equals ax squared because I knew it was quadratic, and the rest of the work was just me trying to figure out what a is. And I did that by finding a point that's not on the vertex, plugging in the x, plugging in the y, and then found it was negative 1/8 and able to finish it that way. Last one I want to do with you is number 31. 31 is not linear. Should be obvious. You got this curve. It's not quadratic because it's not symmetric. You don't have this U shape. This has got to be exponential. So you're going to want to memorize kind of the basic form of that exponential, which would be y equals some base. I'll use b, you could use a if you want, to the power of x. This is the parent graph form. And you remember it's not drawn in here, but it's there, it's invisible. It's this, you have this horizontal asymptote, which is y equals 0, because all those points on there have a y value of 0, no height. The first point at 0, 1 is kind of it's not the vertex, but it's the point that you don't want to use to help you find b. Okay, we need to find b, and you're going to use the point that's not your parent graph point, which here would be 1, 1, 2, 3, 4, 5. So 1, 5. So you plug in 1 for x and 5 for y, and solve for b. b to the first power is just b, so we end up with 5 is equal to b, and so we know what b is, so we finish by plugging that back in, and we end up with y equals 5 to the power of x.